Good morning, good afternoon, good evening. Today we're going to be talking about directional cosines with vectors. We can now talk about directional cosines. Now, directional cosines can be very confusing. What you really need to know is the formula and how to use it when this is all done. Let's take a look. Here we have, in 3 dimensions, the vector r. It goes from our origin 0 or O out to P. It's got an x component, a y component, and a z component. So OP is equal to vector r, which is equal to x1i in this direction. I is coming out. We have a little chart here to show you that I is coming out, j, or the y direction, this way, and k is vertical. So it's equal to xi plus yj plus zk. So it's xi, yj, zk gets me the position vector. Remember, position vectors start with their tail at the origin. Well, here are our angles. Alpha, beta, and gamma are the angles on R. Alpha is the angle in this triangle, OAP. It's coming out of the board at us. Beta is the angle between our vector R and the y-axis, and gamma is the angle between vector R and the z-axis. Well, cosine alpha between our vector and the x-axis is equal to, well, if I consider the triangle OAP, what's cosine? It's adjacent over my hypotenuse. Our adjacent here would be x. So we'd say that this is equal to x over the magnitude of r. And cosine beta, if I think about closing this triangle here, OBP, cosine beta is adjacent over hypotenuse, which would be y over, I'm going to use the magnitude of r. And finally, cosine gamma is equal to, if I close this triangle up here, OCP, then cosine gamma is equal to adjacent over hypotenuse. Well, we know our hypotenuse in this case is the magnitude of r, and our adjacent is this line here, which happens to be z. So we get cosine alpha is x over the magnitude of r, cosine beta is y over the magnitude of r, and cosine gamma is z over the magnitude of r. Please stick with me. Continuing on with directional cosines, we know that the unit vector of r is r hat, and r hat by definition is the vector r divided by its magnitude. So we can say r hat is equal to 1 over the magnitude of r times r. Those two are equivalent statements. And we know that r is really xi plus yj plus zk. So we can substitute that for r. And finally, we can distribute our 1 over the magnitude of r times xi plus yj plus zk. And when we do that, we get xi over r plus yj over r plus zk over r. Well, what was x over the magnitude of r? It was cosine of alpha. What was y over the magnitude of r? It's cosine beta. What's z over the magnitude of r? It's simply cosine gamma. Please just stick with me. This is a long process to get at our final formula. Well, if you're with me this far and you can accept this, then you realize that r hat is my hypotenuse. And then I can use the Pythagorean Theorem. This squared equals this squared plus this squared plus this squared. We can write these squareds in between the cosine and the actual angle, and 1 squared is just 1. Well, we call cosine alpha L, cosine beta M, and cosine gamma N. So we wind up with this statement: 1 is equal to L squared plus M squared plus N squared. We can then ask ourselves an important question. What does all of this directional cosine stuff mean? Well, if I have a vector A in 3 dimensions, call it its component x1i plus y1j plus z1k, and a vector B in 3 dimensions, x2i plus y2j plus z2k, then L is simply, if you remember, is the cosine. So it's the x component over the magnitude of the vector, which was our hypotenuse in our last picture. So that's x over the hypotenuse, plus our m here is going to be our cosine of the y component. So that's y over the magnitude of a. And our z component is called m, which is the z component over the magnitude of a. The same thing happens with b. L, again, is the x component over the magnitude of b. M is the y component over the magnitude of b. And m is the z component over the magnitude of b. Remember, from our last 3D picture, these are simply the cosines. Well, I can then conclude that cosine theta is equal to L1 times L2 plus M1 times M2 plus N1 times N2. We're almost at the point that we need to be. We're getting close. Remember this. Okay, bear with me. We're getting real close now. We saw in our last slide that cosine theta equals L1 times L2 plus M1 times M2 plus N1 times N2, which worked out just to be the cosine of the x component, which was x over A, times x over b. These are both the cosines of the x component of our two different vectors, a and b, plus the y component over a times the y component over b. Notice these are the magnitude of a and the magnitude of b, plus the z component over a magnitude of a times the z component over the magnitude of b. When you put it all together, if we have this over the common denominator over the magnitude of a times the magnitude of b. Don't forget, to find these, we're just using the Pythagorean Theorem. Finally, we get cosine of the angle between two vectors, a and b, in 3 dimensions, are x1 times x2 plus y1 times y2 plus z1 times z2. x1, y1, z1 comes from vector a, for example, and x2, y2, z2 come from vector b. Find the magnitude of a using the Pythagorean Theorem. Use the Pythagorean Theorem to find the magnitude of b. This is what's important. This is the final, after all that work, this is what you've got to remember right here. And you use it to find the angle between two vectors in 3 dimensions. Look at how all of this comes together now. Earlier we learned that the dot product, the scalar product of a and b, could be simplified by x1 times x2 plus y1 times y2 plus z1 times z2, where the x component of a is x1, the y component of a is y1, the z component of a is z1. So x1, y1, z1 correspond to vector a. And vector b is x2i plus y2j plus z2k. So x2, y2, z2 belong to vector b. We saw that already. And then I said the dot product can also be written as a dot b, or the scalar product can be found with the magnitude of a times the magnitude of b. Again, you just use Pythagorean Theorem to find them, times the cosine of theta. And I said the most useful thing we do with this is solve for theta, or solve for cosine theta. Cosine theta is equal to divide both sides by the magnitude of a times the magnitude of b. And we got this. We saw this before. Well, now let's combine the two. We could say that if the dot product of a and b is x1, x2 plus y2, y2 plus z1, z2, we can substitute in the numerator there and get what we just got in that long-winded example. So you should know these 3 things. And this is just the combination of those two. Consider vector A, 2i minus the square root of 2j plus k, and vector B is negative 1i plus 2j minus 1k, both of them in 3 dimensions. Part A, find the directional cosines of vector A. Well, we know that A hat, or the unit vector, is the vector divided by its magnitude. How do we find its magnitude? This is vector A. We simply have to do the Pythagorean Theorem. 2 squared plus negative square root of 2 squared plus 1 squared. Square root will give us the square root of 7. Well, on top we have the vector itself, 2i minus the square root of 2j plus 1k. There it is. Now, if I divide square root of 7, square root of 7, square root of 7 3 ways, I get 2 over the square root of 7i. That is your directional cosine in the x direction. It's also known as cosine alpha. Then negative square root of 2 over square root of 7j. Well, this is the directional cosine for the y direction. That's cosine of beta. And the third directional cosine is 1 over the square root of 7. That's cosine gamma, and that's for the z direction. So there are your 3 directional cosines. So we found our directional cosines for vector A. Let's do the same thing for vector B. Find the directional cosines of B. By definition, B hat is our unit vector, which is, by definition, the vector itself divided by its magnitude. The vector itself is negative I plus 2j plus negative k, which is x direction, y direction, z directions in 3 dimensions. Divided by its magnitude is Pythagorean Theorem. Negative 1 squared plus 2 squared plus negative 1 squared works out to the square root of 6. Well, divide square root of 6 into negative 1, into 2, and negative 1, and you get, here are your directional cosines. Negative 1 over the square root of 6, 2 over the square root of 6, negative 1 over the square root of 6. Once we know the directional cosines, then finding the angle between A and B is rather easy. It's just directional cosine in the x direction times directional cosine in the x direction for the two vectors. Directional cosine y times directional cosine y, directional cosine z times directional cosine z, which just amounts to this times this, plus this times this, plus this times this, which you can see here. Of course, our common denominator is going to be the square root of 42, and ultimately we get negative 3 minus 2 square roots of 2. Alternatively, with this same problem, we learned that cosine theta is equal to the dot product A dot B divided by the magnitude of A times the magnitude of B. Well, what is A dot B? It's simply x times x right there, y times y right there, z times z right there, divided by magnitude of A, use Pythagorean Theorem, square root of 7. Magnitude of B, find that, square root of 6. This is probably a lot easier to use when you're asked to find the angle or the cosine of the angle between them. If I wanted to find the angle now, I just have to take arc cosine of both sides of this final answer. This is probably a lot easier than remembering these directional cosines.